Allow me to introduce myself. My name is Mr. Gould Williams. I'll be joining you guys very shortly at St. Leonard's. Today, I'll be doing your lesson on astronomy. So before starting at St. Leonard's, I was an astrophysicist. So this stuff is right up my alley. I used to work at a planetarium as well, so I love talking about space. So I feel very fortunate that I get to speak to you guys, year 9, about this. So if you ever see me around, I might teach you guys, I might not. But if you see me like walking around the corridors, that's who I am, Mr. Gould Williams. Space is my business. So yeah, let's get on with things. So first things first, I'm going to share hopefully all of my screen with the whole presentation. Fingers crossed that this is working. Now let's get started. So for today's lesson, what we're going to do is we're going to start off recalling some of the stuff that we've learned already in some of your previous lessons. So you've learned about Doppler shift, or the Doppler effect. So what I want you guys to do is you should be able to find on the shared document where you found this video a worksheet to go through, or if you'd rather use pen and paper, feel free to use that. So what I want you to do is answer these 2 questions by here. Give yourselves 2 to 3 minutes to do that. Because this is a pre-recorded lesson, what I'm going to encourage you guys to do is to pause the video, answer the questions in your own time, and then continue to watch the video afterwards. So question 1 is, what is the Doppler effect and when does it occur? And the second is, give an example of when you might hear the Doppler effect in your day-to-day life. So again, pause the video now. Give these 2 questions a go, and what we'll do is we'll carry on in 5 seconds. So pause the video now, answer the questions, pen and paper, or on the document. So we'll carry on in 5, 4, 3, 2, and 1. So I'm going to assume that you've done the questions. These are the answers. So this is some recall from one of your last lessons. So the Doppler effect is when there's a change in frequency and wavelength of a wave, is what I should have included by here. That's an important point. So when a wave, when there's a change in frequency and a wavelength for a wave, and it only happens when the wave source is moving towards or away from an observer. So the common example, so that's question 1. The common example is with some sort of siren. So I wrote down an ambulance. When an ambulance drives past you, in this example, there's like a little police car, and as the car is moving towards this gentleman right here, the waves get squished together, so the frequency increases. However, for the lady over here, the waves essentially get stretched, so the frequency goes down, the wavelength goes up, and the wavelength goes down for the gentleman by here. So what are we going to be learning today? So it's important, I think, to consider what we've learned so far. So you guys have learned the history of astronomy, the structure of the solar system, and considered just how big space really is. You've looked at a couple of different types of telescopes, I think I saw in one of your lessons, and in your last one, you've thought about Doppler shift. Now, have a look at the keywords at the bottom by here. These are what we're going to be using to answer some questions towards the end of the lesson. And what we're going to be focusing on is the life cycle of stars. I think this is a tremendously interesting subject. And also, now I'm not going to focus too much on this, but I think it's still something quite interesting for you guys to look into. Towards the end of the lesson, we're going to be looking at what sort of evidence there is of that stellar evolution. So let's begin. Before we do, looking directly at the stars, what we need to understand is how stars burn. Now, for the longest time, people thought that stars burnt just like, you know, things burn on the Earth, with a fuel, oxygen burning, and hey-ho. But the problem is fuel runs out really quickly when you burn like that. And so scientists back in the 1800s knew that the sun's been around for thousands and thousands of years, possibly more, they thought. So it can't burn the same way as a fire. I think they did calculations on just how big the sun was and calculated how long it could burn for, and the math didn't add up. And what we eventually found out was that something called nuclear fusion is what's going on inside of the center of the star. Now, this is a definition. I've got some little signs, symbols in the top right corner, what you need to write down, what you don't need to write down. So I think this is an important definition of nuclear fusion. Feel free to pause the video, get at least the beginning of this definition by here. So nuclear fusion is when two small light nuclei join and then to make one heavy nucleus. That's a core definition. That's the textbook definition. And this is the way that stars burn. So in the example below, we've got two types of hydrogen, one nucleus of a hydrogen atom, and here we've got what we call an isotope of hydrogen here. So it's got an extra neutron. They combine and they form an isotope of helium. So we've got hydrogen plus hydrogen equals helium. And I know that this looks very, very complicated. I mean, it might not. I know you guys are really, really smart. But all you can think, if this definition is intimidating, it's when atoms touch. So usually atoms never touch, but in the center of stars, there's so much gravitational force, there's so much pressure from gravity that the atoms themselves touch, and when they touch, this process by here, it releases a lot of energy. Now that we know this, so think nuclear fusion by here, that's when atoms touch, they create heavier elements, and they release a tremendous amount of energy. We can start thinking about, so we can start looking into the life cycle of stars. Now, something I used to like saying when I used to work at the planetarium was that stars are like people. They're born, they grow, they live their lives, they get older. And as they get older, they tend to fart. They release gases. And you'll see what I mean about that a bit later. So let's have a look at the two types of stars. In reality, there's only two types of stars that we're going to consider. We've got the normal heavy stars, and then we've got the super heavy, ridiculously heavy. Now, I think a more accurate definition, title would be low mass stars and high mass stars. Now, here we've got the sun, and you can see it compared to, there's the Earth, here's Jupiter, and then there's the sun. The sun is tremendously big. Now, here we've got an example of a high mass star. Now, there's the sun, there's a blue giant star called Rigel, and then we've got a blue supergiant behind it called R136A. The names aren't very inspired. However, the one thing I love about astronomy is that the names are relatively straightforward for the classification. So that's a blue giant. That's a supergiant. It makes sense. So we're going to be considering low mass stars like our sun, and then we're also going to be considering much heavier mass stars like Rigel. So these are stars that are 5-10 times the mass of our entire sun. So they're very, very, very big. So let's start off with a small, I'm going to say low mass star like our sun. So they start their life off in what we call a nebula. Now, a nebula is just a large collection of gas and dust. Now, eventually, gravity is going to pull that dust cloud together, and it's going to essentially collapse, and it's going to form what we call a yellow dwarf. That's what we call the sun. It's a yellow dwarf because it's relatively small. Now, the sun, if you look, it's not going crazy. It's balanced, so it's stable. So we've got a stable star by here, and it's stable because the gravitational force of the entire sun, sort of squishing inwards, is balanced with the nuclear force going out from the core. So in the core, in the middle of the star, that's where nuclear fusion happens, and it releases a lot of energy. And when that nuclear energy is balanced out, when that nuclear force is balanced with the gravitational force, you've got a stable star. So when I'm going to say gravity is equal to fusion by here. So this is force. So when gravitational force is equal to the force of fusion. Now, eventually, what's going to happen with our sun is as it gets older. So after about 10 billion years, of the sun existing, what's going to happen is the hydrogen so the nuclear fusion example that we looked at. So the hydrogen merging to form helium. It's going to run out of hydrogen eventually. And when there's no hydrogen, what happens is it starts to do a different form of nuclear fusion. And that nuclear fusion, so I think it burns lithium, heavier elements like that, and helium. It's going to increase the force from that nuclear fusion. And it's going to be much, much bigger than the gravitational force. And it's going to become unstable. And what's going to happen is that because of that much, much bigger, I'm going to draw by here, because nuclear fusion by here is much greater than the gravitational force, what's going to happen is the sun's going to grow. It's going to grow into a red giant. Now, when it grows, the core shrinks because of that different type of nuclear fusion going on. And also the star itself, the temperature goes down. So it cools down. So there's temp and arrow going down. Now, I've got this little symbol by here. Don't feel like you have to write all this down. Just sort of pay attention. I know I'm waffling on. I know I'm rambling, but I think this is quite cool stuff. So eventually, after about 1 billion years of the sun being a red giant, it's going to run out of even more fuel. So it's going to burn through the heavier elements, and it's going to get all the way up to iron. And when it gets to the point of iron, it can't do any nuclear fusion. So that's the highest, heavier elements that it can get to in a normal star like the sun. And what's going to happen is it's going to shrink a bit, but then it just sort of gives up. It ejects all its gas, and it becomes more unstable, and eventually it sort of farts all of its gases out into space, and it forms what we call a planetary, and then the word that's being hidden underneath this white blob is nebula. So it forms a planetary nebula. And what's left, that white blob, is the core of the dead star. It's a white dwarf right here. And that is the core of the dead star. It would be much, much smaller than this. It would be ridiculously small. I can't think off the top of my head how small it is, but it's small. It's much smaller than this dot, this circle would be. So over time, this whole process would take roughly 10 billion years to happen. So a really, really long time. So for the sun to get to be born from a nebula, to turn into a yellow dwarf, to eventually run out of fuel, turn into a red giant, and then eventually turn into a white dwarf. That would take about 10 billion years. And the sun's about 4.5 billion years, give or take. So this is a long time away. Now let's have a look at high mass stars. So similarly to low mass stars, they're born in nebulas. So a big collection of gas and dust. And again, what's going to happen if this is a much bigger nebula? You'll get a blue giant. So the fact that there's more stuff to burn, the fact that this is a heavier star means that it's going to be hotter. So heavier stars, the temperature is much, much higher compared to lower mass stars. So I think, the sun burns at about, I can't think off the top of my head, about 8,000 degrees Celsius. But a blue supergiant, it would burn about 30,000. In the cores, it's in the millions. So it's a similar process in the blue giant. You've got a core. This is where nuclear fusion happens, and it's burning a lot more rapidly. So it burns really, really quickly, which is why it's so hot, because it's just so high, so massive, so heavy. I don't want to say heavy. It's got so much mass, but it's relatively stable. You've got the gravitational force again being equal to the nuclear force being released. But after a couple of million years, what will happen is it will run out of fuel. The nuclear fusion, the force from that is going to be much bigger than the gravitational force. And what's going to happen? It's going to turn not into a red giant, into a super red giant, or a red supergiant. Now, this star is actually surprisingly unstable for completely different reasons than the nuclear force and gravitational force. Is just because it's so big. So if you placed a red supergiant in the middle of our solar system, it would stretch all the way to the orbit of, I think, Saturn, maybe even Uranus. So it's tremendously big. But what happens is you've got that core, it shrinks again because the star has expanded and a different type of nuclear fusion is going on, and it burns through its fuel rapidly. And once it gets to iron, it stops reacting. There's no more nuclear fusion going on. So all of this force starts pushing downwards like this. Now, the thing is, because this star is so much heavier than, is so much more massive than the sun or the low mass star, what happens is it kickstarts more violent forms of nuclear fusion. So you start getting nuclear fusion releasing elements like gold, silver, much heavier elements. And what happens is as it sort of as the star sort of collapses, you get a really super dense spot in the middle until all that mass is concentrated into one singularity. And what happens is, because this nuclear fusion reaction is so violent, you get something called a supernova, and it is ridiculously violent. It shines brighter than an entire galaxy when a star goes supernova, and you get all the heaviest elements when this happens. And what you're left with is something that's really famous in pop culture. You get a black hole, very famous, and it's a point of infinite density. You don't have to worry too much about what this means, but you know, if you're interested, I think it's really cool to know infinite density, a real life object having an infinite value because it's in a singularity, because it's happening in a point. Anyway, all you need to know about black holes is that no light can escape it. I'm not going to write that all down. No light, actually, can escape, which is ridiculously cool. I don't want to spend any more time on this. I'm sure you guys are sitting on your hands waiting for something to do. So I've got a short little activity for you guys to do. Here I've got a table that summarizes all the information that you guys have just learned. Not in terms of information, but in terms of sort of labeling things, so remembering names. So I'm sure this is something that you guys might be able to do in literally a minute. So copy the table down, or use the worksheet that I've got for you guys. Rapidly fill this in. Pause the video now. Just fill in the gaps. I've filled in some of them for you guys. Good luck. And I'll see you guys in 5 seconds. So pause the video now, fill this in, and I'll see you in 5, 4, 3, 2, 1. So I'm going to assume you paused the video. So let's have a look at the answers. So both low mass and high mass stars are born in nebulas. The middle stage, the main sequence of a low mass star is called a yellow dwarf. I don't think many people know that. The final stage of a high mass star is a red supergiant. Just adding the word super to it, not that complicated. The death of a low mass star is a slow release of the outer layer, otherwise known as farting. Death of a high mass star is a supernova, otherwise known as a violent fart of a star. You just got to keep yourself entertained. I'm so sorry. Now, I can't remember if I mentioned this. You're not just left with a high mass star. Sorry, for a high mass star, You're only left with a black hole if it's heavy enough. Otherwise, you're left with something called a neutron star, which is essentially a giant atom. If I didn't mention that, you'd only know this if you're a big science buff. You might have heard of this from like science shows, Brian Cox or Kurzgesagt. Anyway, and finally, we've got a white dwarf for the remnant of a low mass star. Excellent. So what I think is quite nice, if you literally did that in like 30 seconds, what I'd encourage you guys to do is copy down this sort of diagram by here. It's very, very, very good because it summarizes everything that you just learned in one nice picture. So I'm going to say a little asterisk by here. If you completed the work really quickly and you love this sort of stuff, I'd encourage you guys to do this. Copy this down in like your worksheets or your workbooks, whatever you've got. A little note to add maybe would be that for a main sequence star, for these guys, we'd be talking about billions of years or 10 billion years. And then for low mass, a super high mass star, we'd be talking, you know, about 50 million maybe. So a very, very rapid process. Here, the temperature is low. Here, the temperature is higher. And the same for these guys by here. The temperature decreases when it gets, it turns into a giant or a supergiant. So something that you're going to be expected to do in your GCSEs in however many years it's going to be that you guys have to do that is answer GCSE questions. Now, you're probably going to get a mixture of like multiple choice or like, you know, true or false, whatever questions, or, you know, give the right answer questions, but you'll also be asked to answer 6-mark questions. I'm sure you've done this to death. I'm sure at this point I'm teaching you guys to suck eggs. But while I'm teaching you guys to suck eggs, I think an important distinction for you guys to understand is when an exam question, it might ask you to explain something or to describe something. So I think it's something that a lot of people struggle with. So when you're explaining and describing, I think a lot of people get muddled up. So if an exam question, a 6-mark exam question, asked you to describe this graph, so you'd literally be saying what you can see. So you'd be saying, there's a linear sort of bit by here. So it's straight, I guess. If you don't know the word linear, I'm sure you guys probably do. And then it goes flat at the top, or it plateaus. So you're literally describing the line. Whereas if you're asked to explain this graph, you'd be expected to read the scientific data. So, you know, you've got light intensity. I chose this graph by, you know, that random. You know, you should be able to understand this. Anyway, so here you've got the rate of photosynthesis, light intensity. So you could say, light intensity, if you increase that, you increase the rate of photosynthesis. More explanation, and you might explain the theory behind that, why that might happen, why you get this flat top. So similarly, you'd be asked a question like this, perhaps with astronomy. So let's have a look at a 6-mark question in a astronomy question. So here you're asked to describe what happens to a star much bigger than our sun once the star reaches the end of its main sequence period. Your answers should include the names of the stages the star passes through. So, and that's 6 marks. Now, you wouldn't write an essay just haphazardly. You'd be expected to plan. So I'd encourage you guys to think at least of a short structure, because your answer has to have some sort of logical order. And, you can't be going all over the place when you're describing this process. You've got to describe things in detail, and you've got to cover the key concepts. Now, in this question, they gave you the key concepts that you have to cover. So it should include the names of the stages. So you know already what they're looking for. You'll know what the examiner is going to be looking for. So let's have a quick, actually, no, let's look at every single detail that you could point out in this question. So describe what happens to a star much bigger than the sun once the star reaches the end of its main sequence. So when it gets to the end, when the star's dying, so you could say that the star runs out of hydrogen, it expands to form whatever the name is, the core shrinks, helium starts to fuse with other elements. There's the name, red supergiant. So you've got a lot. The fact that it goes supernova, it becomes a neutron star or a black hole. So you've got a lot of things to cover, and listing it like bullet points like that could be quite intimidating. But the thing that's important to remember is you're getting 6 marks. So you've got to make sure you've got at least 6 points to your answer. So here we've got, I think, a really good answer. So as the star starts to run out of hydrogen, there we go. You've already mentioned that. You've mentioned hydrogen. It cools, excellent work, and expands to form a red supergiant. There we go. It expands to form a red supergiant. You could get a mark for expanding, I'm not sure. The red supergiant will eventually explode as a supernova, another point, forming heavier elements, another point, of becoming a neutron star. Its mass is large enough, the core will collapse to a black hole. So here we've got literally just a paragraph. I think that's 3 sentences there, but it's jam-packed with information. I think you guys are more than capable of writing down an answer like this. So feel free to pause the video, read through that a couple of times, make sure it makes sense in your head. Now, what I'm going to ask you guys to do is answer your own 6 marker. So here, describe in as much detail as you can the life history of a star like our sun. So what's the difference between this question and the question we just looked at? Have a look. Both of the questions are in your exercise sheets. Feel free to just answer this one if you really want. You could maybe write your own answer for this. It's usually good practice. And I'd say good luck. Don't spend more than 10 minutes on this. Pause the video now and come back when you're done. So we'll carry on in 5, 4, 3, 2, and 1. Excellent. So I think something to bear in mind. So that's the main part of our lesson done. We're coming to the end now. I think something important to bear in mind is why do we study science? And I think it's really important to just note how many new things are happening, how much new science there is for you guys to discover and to participate in. Now, you'll all be aware of the Mars lander Perseverance. This is one of the new frontiers of science, and it's landed on Mars. It's landed in what was an ancient lake, and it's looking for microbial life or signs of long lost life. And I think something that's quite marvelous is to think about the masterwork that required to be put in to get this to work. So here we've got the rocket lander, and then it's sort of with a crane lowering down this lander by here. Now, the size of this, I think a lot of people, it gets lost in translation, but you would be about that big. I mean, depending on how tall you are, it might be that big. But this thing is about the size of a car. It's humongous. And they managed to, remote control it with a 15-minute delay, and land it on a planet like this. It looks ridiculous. It looks unreal, but they managed to do it. And there's going to be a tremendous amount of science that comes out of this. There's also the James Webb Telescope is going to be launched soon. So this is a type of telescope, and it looks, I wrote for IR, this is infrared. So it looks in the infrared range of the spectrum to make observations, and it's going to be looking for the earliest formed galaxies, and it's going to be looking through dust to find star-forming regions. So it's going to be looking for baby stars, and it's going to do research into star formation, the life cycle of stars, just like we've been studying today. And again, thinking about how big this thing is. So you would be about the size of this. These are gold-plated hexagons, and they're essentially like a giant mirror reflecting heat into this little point just up by here. And the size of this telescope is about the size of a bus. It's humongous. So there's going to be lots of interesting science from that. There's also the LIGO detector, and this detects colliding black holes. There's also thinking about the Big Bang. Why did the Big Bang bang? I think that's quite an interesting question. You've also got quantum gravity. So quantum mechanics and gravity don't really mix together. So we need to find a unifying theory. You guys might be that person who finds that unifying theory. There's also string theory. There's lots of interesting science that you guys can go into. But that's going to happen in a couple of years. That's going to happen when you guys go to university, when you study science. But what can you do now? So I wanted to focus at the end of this lesson at what you can do with astronomy. So one of my favorite quotes is that it's the most accessible science. You could do so much astronomy at home. There's this app called Stellarium. Get it, please. It's free. There's also Star Tracker. There's lots of really good apps. And you could do really good astronomy with just a pair of binoculars like this. And look how happy this lady is. And looking at the stars. Fantastic. She's having a tremendous time. Sorry, I'm getting a bit carried away here. What you can do is you can look for a constellation. This is some astronomy that I've done. I feel like an idiot sometimes. But I managed to do this with a relatively cheap telescope, about 70 quid. I managed to take a picture of Jupiter. And look at that. You can see the bands by here. You can see the 3 Galilean moons. I took a picture of this. So that's Saturn. That's Jupiter. That's when they were in or closest approach, when they were really, really close together. Fantastic stuff. And that's something that I could do. So if I can do it, you guys can. But what I want you to do is any time in the next few days when you've got a really cloudless night, what I want you to do is to go outside, and I want you to look for a constellation that looks like this. It's very, very easy to find. It's called Orion. It'll look like that. And you can find it really, really easily by looking for these 3 really, really bright stars. It's called Orion's belt. And it forms this sort of shape, and it is it's Orion the Hunter. Now, the reason why I bring this up is because this is actually a really good constellation to do some really cool observation of stars with. So this is what it would look like in real life. You've got those 3 stars, 1, 2, 3, 4, and this is the constellation here. And also, you can follow Orion's belt upwards and you'd find Mars. I won't focus on that for now. If you want to know how to find planets, talk to me when we get to school. So what you can do is you can find just below Orion's belt, with a pair of with a telescope, you'd find a sort of fuzzy blob. Now that thing is the Orion Nebula, and this is a star forming region. There's lots and lots of baby stars. You can see these reddish sort of stars. These are baby ones, and you've also got blue ones. These are huge, humongous young stars. And that is in this constellation by here. And eventually, it'll turn into a star like this one by here. So this one's called Rigel. And that is a blue giant. I think we looked at that star at the beginning of our lesson. But eventually that star will become a star like this. This is Betelgeuse or Betelgeuse. I can't think how to spell it, so I'm not going to bother. There it is, Betelgeuse. So the bottom right is Rigel, and eventually it'll turn into a red supergiant like Betelgeuse. And one day, maybe tomorrow, maybe next year, maybe in a decade, Betelgeuse is going to go supernova, and it'll turn into something like this. This is the Crab Nebula. This is the supernova remnant. And one of these little dots by here is a neutron star. Ridiculously cool stuff. So part of the evidence of what we've just learned today is you can get a telescope or you can get a pair of binoculars and literally look at them. You can literally see it. And there's some really cool videos. You could see, a time lapse of a supernova. Lots of really, really cool stuff. Anyway, I think we've gone on long enough. I think a good exercise, as always, to finish our lessons would be a quick, short plenary. So what I want you guys to do, using the keywords at the bottom by here, see if you can complete the sentences by here. I hope you guys have enjoyed this lesson. Pause the video now. I've pretty much finished. Give these few questions a quick go. Have fun. I'll see you guys really, really soon. Hopefully I'll get to teach some of you guys or just see you in general. Good luck. Stay safe. I hope you guys have enjoyed this lesson. I'll see you guys very, very soon. Ready? Goodbye.